Next, Spinopic coupling is very important in magnetic materials, and you know the Spinopic coupling. I believe you already studied in quantum mechanics. As you know, in atoms, and there is a nucleus in the center of the atoms, and the nucleus and the electrons moves around and revolving around the nucleus. For example, electrons moves like this, and let's consider for the single hydrogen atom. But this is a nuclear frame. This is a reference frame, not a real frame in the quantum in the relativistic relativity theory of relativity, and every motion is relative. And in this case, in the electron frame, it is a nucleus frame. In the electron frame, electron is inside of do not move, and the atom moves around the electron. And the atom nucleus moves around like this. Also in the electron frame, nucleus orbits around the electron, and the electron do not move. Electron does not move, and therefore the atomic nucleus revolving around the electron, they gives rise to the magnetic field. The orbiting nucleus gives the magnetic field, and like this magnetic field like this, for example. And in from special relativity, the magnetic field can be generated like the velocity v, and the electric field cross v over c. It is a CGS unit. From the theory of special relativity, the magnetic field can be written down like this. And as you know, the electric field is the negative gradient potential. And for the radial potential, in this case minus all direction dv all dr, it is electric field. Spinopic interaction is that Hamiltonian of the electron. Hamiltonian of electron due to interaction between magnetic field and spin. We call it is Spinopic coupling. Spinopic interaction. What is that? There is a spin of electron here, but here in electron frame, nucleus moves around the electron, and they gives rise to magnetic field. And the interaction between the spin of electron and the magnetic field is originating from the angular momentum of nucleus. Therefore, it is a Spinopic interaction. Therefore, here Spinopic interaction Hamiltonian is like that, minus m dot p. But we should consider in here it is 1/1/2, and 1/2 is very tricky to calculate. And anyway, we do not consider for the 1/2. We do not derive the 1/2, but it is the 1/2 is coming from the relativistic Thomas vector. Relativistic Thomas vector, and the magnetic moment can be write down as GE over 2 ME. Here, so M means that magnetic moment, and ME means that mass of electron, CS. This is a magnetic moment. Therefore, here spin-orbit interaction, spin-orbit coupling Hamiltonian is like this, and also because magnetic field is the magnetic field is minus E, and also R equals R dV dr. Therefore, it is that E over here G in electron, lambda G factor is 1/2, and the two cancel with each other, and therefore 2 ME square not ME square, but ME and S dot B. Here B is that M dot B one over C square dV dr, and also R direction cross V. Because E cross V I'm sorry. Magnetic field is that magnetic field is that 1 over C. Electric field is that dV dr and R cross V. Yeah, I'm sorry. Here, because angular momentum is that ME R cross V is the angular momentum, E over 2 ME square C square R dV dr. Here's R, not R hat, but R vector. Therefore, it is angular momentum in like this. In hydrogen atom, the potential is that negative potential is minus E over R, and therefore dV dr is that R square E over R square. Therefore 1 over R dV dr is that R cube E. But here in general case there should have the atomic number G. Atomic number means the number of a proton. Here therefore the spin-orbit interaction, spin-orbit Hamiltonian, can be written like GE square over 2 ME square C square R cube and S dot L. This is a spin-orbit interaction. Here we define that fine structure constant E square over H bar C. Fine structure constant. Then it is that alpha GH bar 2ME square C R cube S dot L. This is a spin-orbit interaction. Here I will describe for Spinopic coupling and Hund rule. And we calculated the Spinopic coupling. Spinopic coupling can be write down like this, and this is energy interaction between the angular momentum and the spin of electron. Actually, this is a nuclear frame. The atoms is in the center of nucleus is in the center of atom and moving around the electron like this. But actually, in electron frame, electron is inside of do not move in the electron point of view, and the atomic nucleus moves around, revolves around the electron. Therefore, here in this case, basically the generating magnetic field driven by the nucleus is the angular momentum, and the spin of electron, there is intrinsic angular momentum is a spin. And there are two possibilities. One is that alignment, parallel alignment, L and S parallel with each other, and the other one is that L and S anti-parallel with each other. And basically then here the total angular momentum is like that L plus S. In this case, it is total angular momentum is maximum. But when we angular momentum and the spin angular momentum anti-parallel case is that minus, therefore it is minimize the total angular momentum. Here we can say that J is maximum case, the high energy configuration, and J minimum case is the low energy configuration. And here let's consider for the L plus S case. Here when we square in both sides, and J square is like that L square plus S square and 2 L dot S. And therefore L dot S is that 1/2 J square L minus L square minus S square in the quantum mechanical point of view, and the J square L square S square is quantized, and it can be written down like this. Therefore, when you substitute the S dot L in this case, and the speed of energy can be written down in this like this in a quantum mechanical point of view, and therefore alpha is the fine structure constant, and it is inversely proportional I cube. Okay. Here in practical purposes, let's write down this parameter is a little bit complex to conceive, and we define that it is a Spinopic coupling constant. It is a strength of the Spinopic coupling, and it is proportional to the G number, and inversely proportional to the R. R is not conceivable because in atoms, and R is very small. And anyway, in the heavy elements like lead or the bismuth, then in that case, then the nucleus atomic size is very large, and the ionic size is very large. It means that R is high, but comparing with increase of R, and the G number is more dominant, and the G number is the high G number, means that high Spinopic coupling constant. Therefore, for strong Spinopic coupling is observed in the heavy elements like lead, bismuth, or the rarest materials. And the heavy elements have the very strong Spinopic coupling. And in this case, we can think about that J should have the spin up or the spin down. For example, in a 2p electrons, 2p means the sp is L equal to 1. In that case, L equal to 1, L plus minus S. Here the 1 electron is that the S is 1/2. Therefore, in the plus case, it is 3/2, and in the antiparallel case is 1/2. Therefore, let's substitute this spinobity interaction in the high spin case. High energy configuration shows that 3/2 3 half plus 1, and the angular momentum and the spin angular momentum. In the it is the energy is that a half the energy, and the other one is that low energy configuration. Low energy configuration J is 1 half, and L is spin angular momentum. When you calculate it, it's minus a. Therefore, in the 2p1 state, there is one electron in the p orbitals, and the p orbitals, 2 energy is degenerated. And but when you apply, in this case, when we turn on the Spinopic coupling, and there is a spin degeneracy lifted. One is that the 1/2 a, and the other one is that the minus a. In this case, angular momentum and L and the spin parallel with each other, and in this case L is anti-parallel with the spin case. Therefore, there is a energy difference, 1/2 a and minus a. Here is the energy gap between this case is that it is minus a and 3/2 a, like this. Anyway, and the Spinopic coupling constant directly measurable from the doublet structure of a spectra, and because the energy level spacing, energy level degeneracy can be observed from the spectroscopy, whether something like that, and therefore from the measurement of the spectra we can find that the doublet spin structure of the doublet structure from the spectroscopy. And here, and we think that from the rough approximation, and we define that there is nth Bohr radius. We define that nth Bohr radius like this, and A is proportional to the G4. Therefore, the A Spinopic coupling constant is proportional to the G4, and therefore heavy elements is important for the high Spinopic coupling. And from the quantum mechanical form of the Spinopic coupling is like this. Therefore, when we write down explicit form for the Spinopic interaction when we apply the S equal to 1/2, then it is like this. You do not need to remember this formula, but you can understand the concept of Spinopic interaction. And anyway, and the important rule, you should remember this Hund rule. Hund rule is how to manipulate, how to calculate the angular momentum, magnetic moments. There are 3 Hund rules. Hund rule is very important. The first rule is that maximize spin momentum, and maximize spin momentum is the cause of the minimize Coulomb energy by Pauli exclusion principle. And for example, the first one means that if there is orbitals like this, and each orbitals 1, 2, 3, 4, for example, it is a 2, 1, 0, -1, -2 in the SPD, d orbitals, in the d orbitals. Here, maximize G means that the spin, if the electron resides in this occupy in a certain orbitals, and if the other spin can occupy in the same orbitals but different spin direction, but the different spin direction means that its total spin is 0. How to maximize the spin is that one spin is in orbital, then the other electron should reside in the same spin direction, because the other electron should have the same spin direction, and the same spin can occupy in the same orbitals, and therefore, the other electron should reside in the other orbital. It is Pauli exclusion principle. And you can imagine that when you ride a bus, there are many seats, and some seats are vacant and some seats are occupied. And when you ride when you ride a bus, and you may occupy the vacant seat in the two vacant seat. But the vacant seat, it is a two seats in each row, and left row and right row, and there are two seats. But you prefer to sit two empty seats, one of two empty seats. Yeah, it is the same. In any way, then the other electron, they favor to occupy the other orbitals, not the same orbital that reside previous electron. It is maximize S. It is due to the Pauli exclusion principle, and also the first rule is to maximize S, and second rule is to maximize angular orbitals. And in any way, then what do you mean that maximize angular momentum is that when you resize the angular momentum, you can think that there are several possibilities. One is that one spin is in here, the other one is like this. But in this case, the angular momentum is -1. It is not maximized, and therefore, when the electron resides in the occupy in orbitals, the electron should have the maximum L orbitals at first. Maximum L orbitals at first, and anyway, therefore, it is resolved for electrons in orbits rotating in the same direction, reduce the Coulomb repulsion. And how to understand? And nucleus like this, and for example here, anyway, in the electron point of view, electron is in the center of the atom, and the nucleus revolving around the electron. But anyway, let's think about that. And the angular momentum means that the rotation revolving around the nucleus. And also, let's think about one electron, one atom moves around in this direction. It is a positive. We define it as positive L direction. But in a different direction, when you consider different direction, is the -L. Here, in this case, in some cases, electron can move close with each other. In this case, in this point, there is a strong Coulomb interaction, because electron has a repulsive force. Therefore, they do not favor to the revolutional motion. Rather than they favor to apart. They favor to apart. One electron is in here, the other one electron is in here, in the same direction of a revolving motion. Therefore, in this case, one electron move like this, and the other one electron like this. Therefore, they far with each other. One electron, the other electron is far reaching with each other. Therefore, it is electron in orbits rotating in the same direction, and to reduce the Coulomb repulsion. That is the maximize angular momentum. The third rule is that if the shell is less than half filled, and the J is that may have the anti-parallel direction. If the shell is more than half filled, they should have the positive parallel direction. And anyway, you know that it is to minimize the spin-orbit energy. And for example, you already know that when you consider for the spin-orbit interaction for anti-parallel direction, it is J equal to L minus S case. Is that the anti-parallel case, the energy is lower than the maximum. It is a low energy, and the J equal to L plus S is a maximum energy, and the maximum energy like this. And therefore here in this anti-parallel case, low energy, and the parallel case is a high energy. And as you know, in nature, they prefer to lowering the energy. Therefore, minimize the spin orbit energy. It is natural to J equal to L minus S. What it means that half a field, more than half a field, for example, if the electron, this orbital is 5 orbitals, but 3, 4, it is less than half a field, and in this case, it is half a field case, and the other case, more than half a field means that if there are 6, 7 other more electrons, and the other electrons should have this direction, and it is the third rule is the result from the second and the first and second rule, because from the first and second rule they should have the opposite direction. The spin should have the opposite direction. Therefore, you already know that this direction is the firstly occupied, and in this case J equal to L minus S, but the other electron may have the opposite direction. They should have the parallel direction. For L and S has a parallel direction. Therefore, it is very natural to understand. And anyway, in this more than half a field, then all the spin up state cancel with each other, and the angular momentum is cancelled with each other. And also here in the different direction should consider for the angular momentum, and the angular momentum direction in this case is a different direction, and anyway it is parallel with a spin. Therefore, it is minimized spin orbit energy. And anyway, important thing is that in transition metal ions do not follow the Hund rule and violate third rule because of the crystal field. I will describe what is the crystal field, and because of the crystal field energy, and in the transition metal that have the 3D orbitals, and there is angular momentum quenching that violates the Hund rule. There are two possibilities for the Adams coupling. L means that angular momentum and spin momentum, orbital angular momentum and spin momentum coupling. There are two possibilities. One is that Adams coupling, the other one is a JJ coupling. Adams coupling is that first consider total spin and orbital angular momentum. At first, there are many electrons in atoms, and in this case, each electronic orbitals, let's sum total orbital angular momentum. At first, we call it as a capital L, and each spin, summation of each spin, we call it as a capital S. Finally, and and total angular momentum is that L plus S. It is that Adams coupling. For it is the Adams coupling is considered for the small g value. As I said, small g or the large g, the different thing is that in the large g case, in the spin orbit interaction is more significant. Therefore, in the small g case, Adams coupling and the orbital angular momentum and the spin angular momentums can separate total angular momentum or the total spin angular momentum is first considered. In the high g case, high atomic number case, and each orbitals, at first, they prefer to have the Adams coupling at first. Small s means that each electron orbital and spin, and total J also consider. And then finally, capital J is that each total angular summation of each total angular momentum. it is JJ coupling. And therefore, the JJ coupling is significant for high atomic number materials, and in this case, as coupling becomes significant at first. Therefore, it is a high G interaction. High G materials has a strong spin-orbit interaction. It gives rise to ADAS coupling at first, and then total angular momentum is that each summation of each total angular momentum like this. Yeah, okay. And let's have an example to understand exactly. And for example, in the Mag2+ case, there are 5 electrons in outer shell, and here in the below valence electron is like argon. Argon is because that the orbitals are totally occupied. In the totally occupied case, there is no angular momentum, and the summation of angular momentum and the summation of spin equal to 0. Therefore, it is not a magnetic properties. Only magnetic property is coming from the partial field orbitals, and therefore partial field orbitals is the outer shell. In outer shell has 5 d electrons. D electron means that SPD L equal to 2, 1, 0, minus 1, and minus 2. At first, then because the electron has 5 electrons, or from the Hund rule, the electron occupy in the different orbitals. Therefore, the electrons occupy first, second, third, like this. In this case, all orbitals occupy as a single electrons. In this case, total angular momentum is 0, because summation 2, 1, 0, minus 1, minus 2 is 0, and only have the electron 1/2 times 5 electrons. Therefore, total spin is at 5/2. In the cerium 3+ balance, here cerium 3+ case, it is the valence electron is exactly same with the xenon, and also outer shell have the 1 electron in the F shell. In this case, F means SPD. SPD is 3, 2, 1, 0, minus 1, minus 2, minus 3. In here, from the Hund second rule, and the electron occupied to maximize the angular momentum, and therefore the electron occupied L3 orbitals. In this case, L equal 3, and spin is 1/2, and therefore it is less than half field. Total J is that L minus S, therefore 3 minus 5/2. It is a total angular momentum when you consider it is ADAS coupling. The third rule can understand that J, if the shell is less than half a field, we can understand is J equal to L minus S. Here is we consider L minus S because 1 electron it is less than half a field. If the shell is more than half a field, and they should have the J equal to L plus S. For example, holmium 3+ is a xenon and 10 electrons in F orbitals. And anyway, in here a little bit different is plus. Minus is okay, but let's consider for plus. And here it is minus. Then because the 10 electrons at first occupy 1, 2, 3, 4, 5, 6, 7, and 9, 10, 9, 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10, I'm sorry. Therefore, 10 electrons occupy these orbitals. In this case, the total angular momentum is that the spin up case cancel with each other, and spin down 3 to 1. 3 to 1 is a total angular momentum is 6, And the spin angular momentum is that 1/2 and minus 1/2 cancel. Spin angular momentum 0, 0, 0, and 1/2, 1/2, 1/2, 1/2. Therefore, total spin is 2. Because it is the more than half a field, and the total J is the L plus S. Therefore, it is 8. Okay. This is a thumb symbol. I will describe later what is the thumb symbol. It is important for spectroscopy. And anyway, we can consider for the J value, total angular momentum, like this. It is a thumb symbol. Thumb symbol is like this. It is 2s plus 1 means that it is a degeneracy, because in quantum mechanics there is a degeneracy depending on the spin. And also here L means that represented or angular momentum. If their total angular momentum is 0, is that we call S, and the 1P, 2D, 3F, SPDF, like this. And also here J means that J is the total angular momentum, what we calculated from the Spinopic coupling. And also, for example, in the case for that S equal 1/2 and the L equal to 1 case, the J has the two possibilities in the JJ coupling. And also JJ coupling, the J equal 3/2, the other one is 1/2, and the thumb symbol is like this, because L equal to 1, it is a P, and the degeneracy 2s plus 1 means that it is 2s1 plus, it is degeneracy is a 2, and total J is that 1 is that 3/2, and the other one is that 2p 1/2. Because there are two energy eigenstate, it is degeneracy is a 2, like this. Well, here we already say that there are two possibilities. One is the LS coupling, the other one is the JJ coupling. And the LS coupling can be considered for light elements, and the JJ coupling is the heavy elements. One example is carbon. Carbon is 2p orbitals, and there are 2 electrons in the p orbitals. Low atomic number, because p equal to sp means that sp L equal to 1, 0, minus 1, because there are 2 electrons, spin occupied, electron occupied, spin 1, like this, 2 electrons. Therefore, S equal to 1 and L equal to 1. Because it is LS coupling, total J is the L minus S, therefore it is 0. The thumb symbol is a degeneracy, 2s plus 1 is the 3, and sp is p orbitals. Total angular momentum is 0. The thumb symbol is like this. Because when you see the thumb symbol, total angular momentum is 0. There are 3 orbitals. Then the 3 orbitals like this. 3 degeneracy can be possible. Therefore, in the lead case, and carbon, there are 2 electrons in p orbitals. Then in this case, it is a JJ coupling, and here we know that one electron has the occupy 1, 0, minus 1, and anyway, and here one electron occupy one orbitals like this, and also here the S is that, and 1/2, and L equal to 1. Here in this case there are JJ. Here is the spin, one spin, and the other one electrons like this. And in this case, it is L equal to 1, small L equal to 1, S equal to it is not spin, it is 1/2, and in this case L equal to 0 and spin is 1/2. Therefore here is that the J is that it is 2/3, and in this case 1/2. There are two J value. Therefore, in this case, and total J has that they prefer to have the they prefer to have the low J, and to minimize the spin-orbit interaction. Here they prefer to J1, J2, two electrons. They prefer to have the 1/2 value for J value, and also in this case, and the total J is that J1 plus minus J2 can be possible. In this case, there are 1/2 plus minus 1/2. It is that 0, two possibilities, 1 or 0. And here, total J, 1 is the more high energy, and J, 0 is more low energy. Therefore, they prefer to the 0 angular momentum. Therefore, the total J equal to 0 means that there is no magnetic moment. And here, in this case, L and S is not good quantum numbers, because at first, and small LS coupling is only conserved L1 plus S1 like this, and the J1, and the total angular momentum and the total spin is not good quantum numbers. And also they prefer to the low energy. At first, consider for the possibility for J, and they prefer the low energy. And if the electron has the low energy, and the total angular momentum has the plus minus, and also they also prefer to low energy, low total J value. Yeah. Then the term symbol from the consideration in the previous case, and there are the spin, the J equal to total J is that 30/2. The other one is that 1/2, and because spin degeneracy 2s plus 1, because s equal to 1/2, and degeneracy is 2, orbital sp, like this. This is a term symbol like this.